I'm Campbell, and along with Edith and Monika, we have built a computer vision tool that helps you map the safest and smoothest route from A to B in Berlin. Here's a very quick example of what we've managed to do, with the green dot being Hauptbahnhof, or the main station, and the red dot being DSR, or Eislebnerstrasse. We'll go into a little bit more detail about the different colors that we have on the screen. But for now, I'd just like to introduce you to why we've done this. So in 2021, there were over 6,000 reported bike accidents. The image on the screen behind me is a painted bicycle, which indicates someone has been killed. This is an all too common occurrence or scene in Berlin. And for those that enjoy cycling, this is a perilous situation that we face. Now we are seeing what an average person will see on their commute to work or coming home from work. Sharing a bike lane with a bus, lorry, cars coming in, angry drivers, broken glass, all this kind of stuff. It's not very pleasant all the time. If you're able to survive those streets, then the likelihood is that you'll turn down a side street and be met with another disaster, cobblestones. It's a sensation that we can all, I'm sure, relate to. And if you haven't cycled over cobblestones, I don't recommend it anytime soon. So where are we? In 2020, during the coronavirus pandemic, the Berlin Senate decided to introduce pop-up bike lanes. These are segregated, safer bike paths that oftentimes took one lane of traffic entirely. And this saw a 25% increase in bicycle traffic in Berlin, which goes to show that with safer cycling infrastructure, more people would ride their bikes. And as Jose alluded to, currently mapping systems like Google Maps or Komoot, which is another popular bike mapping software, has no option to actively avoid these cobbled streets or busier roads where you might want to go stick towards like a bike lane instead. Therefore, what we wanted to do was build a tool that did exactly this, that gave you the smoothest and safest route from A to B, avoiding cobblestones and giving preferential treatment to nice, wide, safe bike lanes. So to do this, what we wanted to do was automate how this is done so far. OpenStreetMaps, Google Maps, and Komoot use user hand labeling, so users actually have to actively say when they encounter cobblestones or busy roads and things like that. What we wanted to do was make it automatic. So we used Street View data of Berlin to detect whether a bike lane was visible or not present. If it was, then we would say whether it was, we would classify it as to whether it was safe or less safe. If a bike lane wasn't present, then we would say whether the road is asphalt or everyone's nightmare, cobblestone. So you may or may not be aware that Google Street View last updated their images for Berlin in 2009, and so therefore there's no current pictures available. To overcome this, we found a data source called mapillary.com, and as you can see, all the little green dots there are individual images of Berlin from different angles. It covers the whole city. This is the current coverage of the city. There are over 10 million images of Berlin, so data was in plentiful supply. How then do we go from the map of Berlin covered in green dots to a mapping system that allows us to avoid cobblestones and hazards? So what we wanted to do was take an input image, one of the images that we saw before. As I said, identify whether a bike lane is present or not. If one was present, we would then say whether the bike lane is safe or unsafe. These are labels that we've given them. It's not to say that the bike lanes are unsafe, but they're just less safe than the other ones. If a bike lane wasn't present, then we would then classify the surface to say whether it was a cobbled street or an asphalt road. And with that, I'd like to hand over to Edith, who's going to go into a little bit more detail about our pipeline.
Thanks. So to assess an image, we first examine whether a bike lane is present. We use semantic segmentation to achieve this. The model we choose is a vision transformer mask transformer that has been pre-trained on mapillary with this dataset. This dataset contains 25,000 street view images from around the world. And one of the semantic object categories of this model is bike lane, so exactly the category we are interested in. The task of the semantic segmentation is to label each single pixel of an image. And on the right image, you see colored in magenta a Berlin bike lane segmentation. Okay, Monika will now explain how we further examine an image if a bike lane is present.
So if a bike lane was detected in an image, then the next step is to label it either as a safe or as an unsafe bike lane. However, bike lanes are extremely visually diverse, as you see from these example images. So instead of using a supervised classification approach, we used an unsupervised method, clustering, to use the clustering algorithm to sort the images for us based on the visual features. And then to label a new image, we would compare the new image to the clusters and then label it based on the label that the cluster has that the image is closer to. And how we did this in more detail was that first we extracted embeddings from the images, then we performed the clustering, and then labeled a new image using the clustering. So to extract embeddings from images, we first created a small data set of about 240 images of bike lanes from a pillory, and we ran a forward pass of every single image through a deep neural network and extracted the embeddings at the top layer. This is more useful than using raw pixel values because embeddings have more richer and high-level information that can be used from by the clustering algorithm. As the network to extract the embeddings, we use Dino version 2. Dino stands for distillation with no labels, and it's a self-supervised vision transformer pre-trained on ImageNet, and it provides high-quality visual embeddings, as you can see from the example images here on the right. The second step was then to feed those embeddings into the clustering algorithm, and as clustering algorithm, we used K-medoids. K-medoids defines clusters by finding a central medoid, so a central data point that has the smallest distance to the other data points within the same cluster. And it does so iteratively by finding the medoid that has overall this smallest distance to the other data points. The distance measure we used was cosine similarity. So for example, if you have two images that are very similar, they will have a high cosine similarity and they will most probably allocated to the same cluster. And when you have images that are very different, they will have a low cosine similarity and might be assigned to separate clusters. So after running through these steps and determining that we want to look at two clusters, this is what the algorithm gave us. The first cluster contained mainly images of bike lanes that were on the sidewalk, so separated from the street. So we termed this the safe bike lanes. And the second cluster gave us mainly images of bike lanes that were on the street and only separated from the cars by the dashed line. And on the right-hand side, you oftentimes have parking cars where you could have an opening door anytime. Therefore, this was termed called the unsafe bike lanes cluster. You can also reduce the dimensionality of the embeddings using TSNE to then visualize what the clustering algorithm actually did. And here you can see in two-dimensional space that it pretty neatly separates safe from unsafe bike lanes, also with a few exceptions. The third and final step then would be to use the output of this clustering to label a new image. And the way we did this was to use the central medoids from the clustering. So K-medoids gives us the central data point, which is called the medoid. It's also the most representative image. So when we get a new image, we can use cosine similarity to compare it to those the two central medoids. And then if the new image has a higher similarity to this medoid, then it will be labeled a safe bike lane and otherwise an unsafe bike lane.
So if no bike lane is detected, we examine the surface of the road. So if it's a cobblestone or asphalt surface. For the classification task, we choose convolutional neural network based on the small efficient net V2 pre-trained on ImageNet. And we fine-tuned this model on our hand-labeled data set of around 450 street view images. The class activation map highlights the area which contributes most to the model. So in this, on the right picture, you see that the our model focused on the surface, in this case, in cobblestone surface to predict the surface of the.
Okay, so then we had an output label for each street based on the image classification into a routing system. What we had to do was take OSM and turn it into a network X graph. So we had edges for all the roads and nodes for all the junctions. And what we wanted to do was add the labels to the edges and then turn the edges back into the map afterwards. So as I said, we would take the coordinates of the image and then we would assign that to the coordinates of the edges. And here we have an example of what this showed. So this showed where there are bike lanes present in green, safe ones, where we have unsafe bike lanes or less safe bike lanes in yellow. Blue represents asphalt streets and cobblestones are then highlighted in red. Following this, we then wanted to add weights to these different labels so that the model would find the shortest route there with the lowest weight. Obviously, assigning higher weights to less pleasurable routes, and yeah, the result was that we were able to get a nicely drawn line between 2 points, showing you which surfaces you'd be riding over and avoiding, where possible, inconvenient surfaces.
So in sum, we created a tool that promotes the safest bike route and optimizes the comfort of bicycling by avoiding cobblestones. The next step in this project are that we would like to implement our tool in an actual app so that we can actually use it to go out and bicycle. And we're also interested in looking at the metadata and Mapillary and OpenStreetMaps to add this to the labels that we currently have to label the roads. And explore more categories of bike lanes. For example, some bicyclists might find it important to have a smooth bike lane instead of one that has uneven surfaces. And with this, we come to the end of our presentation. If you're interested, you can look at our GitHub or contact us on LinkedIn. And we would like to thank our mentor, Antonio Rueda Toysen, who's also here. Thank you.